Welcome back. In this shorter lesson, we are going to take a look at some linear algebra concepts that we're going to need in order to analyze systems of differential equations. So I like to call this the linear algebra crash course. So we'll just talk about some of the essentials that we need in order to move forward. So first of all, and the most important concept in linear algebra is the concept of a vector. And we've seen some of these already, but to more formally define them, a vector is a directed line segment whose tail begins at the origin and whose tip terminates at the coordinates specified by the vector. For example, x equals, and notice how we are talking about vectors as opposed to the variable x. When you have a letter, lowercase letter with a arrow over it, that implies that it has more than one component, and we can typically think about these as the x and y components. So even though we still are thinking about this value here as the x value and this value as the y value, we can still call the vector x with an arrow over it, and that's different than what we're calling the component x. So this vector here has its tail and its tip right at this point, and you can see that it starts at the origin and terminates at the point 1, 2. Now that's in standard form. You could also have vectors that start somewhere else. For example, let's say at the point 1, 3, and as long as its displacement is 1 in the x direction and 2 in the y direction, we could say that that vector has the same that's the same vector as the one we're analyzing that's down here at the origin, that's over 1 up 2. So these are actually identical vectors. They don't have to be at the origin. We can perform operations on vectors. We can add them, we can subtract them, we can scale them. For example, if we took 3 times the 1, 2 vector, we get the 3, 6 vector. And an important thing to notice is the change in y over change in x of a scaled vector. For here, it's 2 over 1. For the scaled version of that vector, we have 6 to 3, which is still 2 to 1. So that means that the slope of this vector has not changed. It's still going to point in the same direction, but it's going to triple the length of that vector. So here we have both of those vectors plotted. We can see that the 1, 2 vector is on the same line as the 3, 6 vector, so that effectively just creates a scale effect and not a rotation of any sort. And we can find the magnitude of a vector, or the length of a vector, of x equals, let's say its components are a and b. We can write that as absolute value of x. Now, absolute value just means length of. And so even when you're talking about numbers and you say, what's the absolute value of -2, and you say it's 2, that just means that -2 is 2 units away from relative 0. And so to find the magnitude of a vector, it's equal to the square root of its components squared. To see why that's the case, if you look at this vector here and you triangulate it, you make a right triangle where its 2 sides are its x component and y component. This component is 1 unit long. This component is 2 units long. We can think about this as the hypotenuse, and we know from Pythagorean theorem that the square of the sides equals the sum of the square of the sides equals the square of the hypotenuse. And so c is effectively what we're referring to as the length of that vector. So because c squared equals 1 squared plus 2 squared, c is equal to the square root of the components squared. So that's how you can write the magnitude of, or we'll often call it the magnitude of a vector, but the length of a vector will suffice because we're not going to be dealing with higher dimensions where length doesn't make sense. So we said we can scale vectors, but it doesn't have to be by a constant. The scalar could be a function. So if by scalar, we just mean it's a number. And e to the 3t, even though it's a variable is still just a number. So if we scale the 1, 2 vector by e to the 3t, we're going to scale both of its components by e to the 3t, just like when we multiplied the vector by 3. So that's about all we need to know about vectors for the current moment. A matrix is effectively a collection of vectors. For example, we can write A equals 3, 1, 2, 1, and that is a matrix full of 2 vectors. You can think about them as the vectors 3, 1 and the vectors 2, 1. Now this is a matrix that has 2 rows and 2 columns, so we call it a 2 by 2, and we always say rows by columns. That's just the convention. So if I say 2 by 3, nobody ever confuses that to mean 2 columns and 3 rows. We always are in the convention of saying rows by columns. So matrices can be added and scaled as well. Whenever you add 2 vectors, you might imagine that if I took 1, 2, plus 3, 5, I would just add their components. They would have to be the same size. So this would be 4, 7. And if I were to add 2 matrices together, for example, 1, 2, 3, 4, plus 5, 6, 7, 8, that would simply be 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. So that's how we would add. Matrices, if we scaled a matrix by a constant, so if we took 3 times 1, 2, 3, 4, we would scale its components, and that would be 3, 6, 9, 12. So when we actually multiply, when we conduct matrix multiplication, it's a little bit strange. It's not the way we add vectors or scale vectors or even add matrices or scale matrices. You would think that they would have to first of all be the same size, but here I have a 2 by 2 matrix multiplying a 2 by 1 vector, and what I end up with is a vector that has 2 columns. The column is, remember, this is just one number. 3x plus 2y is a single number, even though it has 2 terms. This is still 2 rows with just 1 column. And the way matrix multiplication takes place in a visual form is the elements of the second matrix multiply or scale the vectors of the first matrix. So here, if you notice that this is the first element in here, if you were to tip over this vector on top, you would see that the x is going to multiply the first column, the y is going to multiply the second column, and then by definition, we're going to add those two together. So x times the 3, 1 vector, y times the 2, 1 vector, add those together. That's how matrix multiplication is defined. We get 3x plus 2y and 1x plus 1y. So already this is giving us a way to represent a system of equations where we could have a matrix that has coefficients in it and then a vector that has the variables in it that maybe we're trying to solve for. As another example, here is a system of equations that is written as a matrix equation right now. So a matrix equation just means that it has matrices and vectors in it, potentially both, maybe just one or the other. And so if we do the multiplication for this, so again, think about it this way, the first, second, and third columns are going to get scaled by x, y, and z respectively, and then those scalar multiples are going to get added together. So x times the 1, 4, 7, y times the 2, 5, 8, z times the 3, 6, 9, those get added together. Now to add that together, x multiplies all the top components, so 1x, 4x, 7x. Y multiplies 2, 5, and 8, so we'll have 2y, 5y, 8y. And z will multiply 3z, 6z, 9z. And then we're going to add those together, add the vectors. So we just add the components of the vector. So 1x will add with 2y and 3z. 4x will add with 5y and 6z. And then 7x will add with 8y and 9z. And remember, that's equal to this vector here, which is this vector over here. And so as a system of equations, this actually means that if 2 vectors, by the way, again, this is 3 rows, but only 1 column, because 1x plus 2y plus 3z is just a single number, that has to equal 7. The second row has to equal the second row. The third row has to equal the third row in order for 2 vectors to be equal to each other. So if we remove the brackets now, and we write it in what's called scalar form, this is just now our system of equations that was being represented as a matrix equation up here. So let's practice this a little bit. Write the system of differential equations dx dt equals 3x plus 2y and dy dt equals 2x minus 4y as a matrix equation. So the first thing I'm going to do is I'm going to write these 2 equations above one another. like this. And now I'm going to wrap them with, I'm basically working backwards from where we ended up in our little example here. So now I'll put some parentheses around these to say this is a 2 by 1 vector equals another 2 by 1 vector. And now what I can do is I can actually think about lifting, again, working in complete reverse. We can now split this apart into the vector 3x, 2x, plus the vector 2y, negative 4y. And then we can factor out an x from the first vector. We can factor out a y from the second vector. And now we can, again, work backwards where in this step from here to here, we conducted the multiplication. So if we were to sort of think about this x, y, and z as lifting back up into the x, y, z vector, the analogy here would be that the x, y lift back up into an x, y vector. And before those columns got scaled, they were part of a matrix with 3, 2 as the first column and 2, negative 4 as the second column. So our final answer here to write this in matrix form would be to say that the vector dx dt, dy dt equals 3, 2, 2, negative 4 times xy. And it's going to be important to actually write a system of equations in the matrix form because we're going to be doing something with this matrix here. Again, this matrix that contains all of the coefficients, this is just called the coefficient matrix. Sometimes you'll see this, that's really the derivative matrix. You'll see it often written like this, dx dt. So it's the derivative of a vector. We'll talk more about that soon. And then we'll just call this here the x vector. That is the vector without the derivatives of x and y in it. So a lot of times you'll see this written as dx, a system written as dx dt equals this coefficient matrix. Usually people write capital Y times the vector x. So now let's work the opposite way. We have a matrix equation. We want to convert it into scalar form. So we want to have x equals equation, y equals equation. So the first thing we're going to do is to bring this into scalar form, we're going to combine all of this stuff into one vector. So scaling 1 and negative 2 by 2e to the 6t will give me 2e to the 6t and negative 4e to the 6t. And then I'll scale 0 by negative 3e to the 2t, which is just going to be plus 0 up here. And negative 3e to the 2t times 2 will give me negative 6e to the 2t. And now I can add these two vectors. So 2e to the 6t plus 0 is just 2e to the 6t. Negative 4e to the 6t minus e to the 2t has to stay like that because I don't have e to the 2t and e to the 6t are not like terms. And so now I can see that x is equal to the top component because the top component needs to equal the top component in the vector. So x is going to equal 2e to the 6t. Y is going to equal negative 4e to the 6t minus 6e to the 2t. And there we have written our answer in scalar form. So now that we know how to work forward and backward, let's look at something that looks at first a little more complex. Define v1 to be the vector 1, 1, v2 to be the vector 2, 1/2. Lambda 1, this is a Greek symbol called lambda. We'll see this arise kind of often. This is lambda. And lambda 1 equals negative 2. Lambda 2 equals 3. The vector x equals just these two scalar components, x and y. k1 equals 5, k2 equals 7. Write the equation vector x equals k1 e to the lambda t. and I forgot this v1 in here, so I just put this in, times v1 plus k2 e to the lambda 2t v2. You will see this quite often, this expression here. So to write x equals k1 e to the lambda 1t v1 plus k2 e to the lambda 2t v2. At first it looks kind of scary, a little bit intimidating. All I'm going to do here is just replace the components with what they are. So the vector x contains x and y in it. K1 is given to us as 5, so 5e to the lambda 1, which is negative 2t. v1 is the vector that contains 1, 1 in it, plus k2, which is 7, e to the lambda 2t, which is 3t. v2 is the vector 2, 1/2. And so now we need to continue to expand this out. So really the purpose of this problem is just to show that we can express it in this, we can express a matrix equation written in this symbolic form, and then we can convert it into actual components. So like before, we're going to write the, distribute the 5e to the negative 2t and the 7e to the 3t. So this will come out to give us 1 times 5e to the 2t, and then 1 times 5e to the 2t again, plus, and then here we'll have 14e to the 3t, and 1/2 of 7, I'll just go ahead and write it as 3.5e to the 3t. And now we add these together, giving us 5e to the 2t plus 14e to the 3t equals x. So the x component is going to be the sum of those, and the y component is going to be the sum of those. And so x will be 5e to the 2t plus 14e to the 3t, and y is going to be 5e to the 2t plus 3.5e to the 3t. And there's our scalar form of that vector, that matrix equation. Another thing we can do with vectors is we can take derivatives and integrals. This might sound scary, but really whenever we perform calculus on vectors, the derivative of a vector is just the derivative of the components. So if we had x and y in here, we take the derivative of x with respect to t, the derivative of y with respect to t, and also the integral of a vector would be the integral of the component and the integral of the other component. So just as a quick example here, find the derivative of this. So the derivative of t squared sine of t is just going to be the derivative of t squared. The derivative of t squared, which we know is 2t, of t squared. And then down here we'll have the derivative of sine of t, which we know is cosine of t. So we'll have the vector 2t cosine t. Simple as that. Now, integral, the integral of this vector will be the integral of the vector t squared sine of t will be, with respect to t, will be the integral of t squared with respect to t, and the integral of sine of t with respect to t. And of course, the integral of t squared is 1/3 t cubed, and the integral of sine of t is negative cosine of t. So that's how we can perform calculus on vectors. That's pretty much all the algebra we're going to be doing on vectors for now, and that's why we call this a crash course. There's a lot of details that we're omitting, but we really just care about having enough to be able to move forward with solving systems of differential equations. So let's take a look at the geometric meaning of multiplying a matrix by a vector. When we multiply a matrix by a vector, we transform it. And transform means just that. You physically change it in some way. Now, in terms of how a vector can change in, say, 2-dimensional space or even 3-dimensional space, is it can get scaled. So it can get stretched, or it can get, if that's my original vector, then you can get scaled. But it can also get rotated. So maybe what happens to that vector when it gets multiplied by a matrix is it gets rotated and maybe scaled. So here we have a matrix A, and the matrix multiplication that we defined above works here. Just we have a coefficient matrix, and this vector just has numerical components instead of having symbols in it. So what we want to do here is find A times X and plot both the new vector and the original vector. So that being said, let's go ahead and start our plot here, since we already have one of the vectors. And so here we'll just say that, we'll kind of scale this. We'll say here's the 1, 1 vector right there. There's our original X. And then now I'm going to perform the multiplication of A by X and see in what way that's going to transform X. So to do that, I have to take 1, 2, 3, negative 1 and multiply it by the 1, 1 vector. So we know from our past experience that this vector and this vector are going to get scaled by this and this respectively, and the results are going to get added together. So we'll have 1 times the 1, 3 vector plus 1 times the 2, negative 1 vector, and really I'm just adding across here because the scalars are 1. So 1 plus 2 and 3 minus 1. So you can see here that now this new vector is at the location 3, 2, which we can see that both of those effects have taken place, that we have both scaled and we have rotated the vector. So 1, 1, that has a length of the square root of 1 squared plus 1 squared, which is the square root of 2, but this guy, the square root of 9 plus 4, this guy has a length of the square root of 13, so that green vector is a little bit longer. So we have a scale and a rotation. Now in a linear algebra class, you talk about different types of transformations and how do you rotate a certain number of degrees or a certain number of radians, and how do you get a matrix to scale your vector for you in a very specific way, but we don't need to get into that here. Now there are special types of vectors that every matrix has. So every square matrix, n by n. So when we say square matrix, we mean things like 2 by 2, 3 by 3, 4 by 4, where there's the same number of rows and columns. Every such matrix has a special set of vectors called eigenvectors and associated scalars called eigenvalues. So how do we know if a vector is an eigenvector? Well, if when you multiply the matrix A by this special vector V, if you only get a vector that is scaled but not rotated, that's the key here. If it doesn't get rotated but it only gets scaled, that vector is called an eigenvector. The value that it is multiplied by is called the eigenvalue, often called lambda. So from above, what we did is we said, take that vector, multiply it by the matrix A. If what you get on the output side is a scaled V without rotation, then, because we've already learned that when we scale a vector, we're basically just going to stretch it or potentially shrink it, but we won't rotate change its direction, then that would be considered an eigenvector. So an eigenvector of the matrix 2, 4, 4, 2 is 1, 1, and we want to show that it's an eigenvector and calculate its eigenvalue. So the question we have to ask ourselves is, if we take AV, do we get a scaled version of the original V? So if we multiply A times V, that's going to be the 2, 4, 4, 2 matrix times the 1, 1 vector, and that equals, again, we're going to multiply the 2, 4 column and the 4, 2 column by 1 and 1 and then add them together. So 1 times 2, 4 plus 1 times 4, 2. We add those together, we get 6, 6. Now if you look at these two vectors in two-dimensional space, 1, 1 is here and 6, 6 is out here. They both have the same rise to run ratio. And in fact, if you factored out a 6, you could see that, hey, yeah, that is just a scaled version of the original vector V. There's the original vector V. Lambda, therefore, must be equal to 6. So we basically, all we did when we multiplied A by V is we noticed that we ended up with a longer vector. So lambda equals 6 is the eigenvalue. Sounds like a fancy name, but all it is just a scalar. It's the scalar by which that vector gets multiplied when it's transformed. Okay, let's do a couple more examples. We're almost done here, and let's show that negative 1, 1 is also an eigenvector to that. So again, what we're going to do is we're going to multiply it and see if what comes out is just a scalar version of what went in. So 2, 4, 4, 2 multiplied by negative 1, 1. So the negative 1 is going to multiply the 2, 4 vector. The positive 1 is going to multiply the 4, 2 vector. And when you add those together, you're going to get negative 2, which is negative 2 plus 4. And then negative 4 plus 2 is negative 2. And at first sight, it looks like, okay, so it's still one of them is negative, one of them is positive, and the components are the same. If I factor out a negative 2 from this, then I can see that that will leave me with a negative 1, 1 vector behind. So negative 2 times negative 1 is still 2. Negative 2 times positive 1 is still negative 2. And we see that what came out is a scaled version of our original vector. And so therefore I can say lambda equals negative 2 is also an eigenvalue. One of the last things that and then not every vector is going to be an eigenvector. So just to show you that I didn't pick a special matrix that just does this to every vector it multiplies. If we took this vector 2, 1, which is not really an eigenvector, but I'll just go ahead and just check this out. 2, 4, 4, 2 times the 2, 1 vector. So once again, the 2 is going to scale the 2, 4 vector. Add that to 1 times the 4, 2 vector. So 4 plus 4 is 8. And 8 plus 2 is 10. And you can see that these two vectors, they don't lie along the same line. In fact, if I wanted to make this component a 2, you might say, well, I could factor out a 4, and this component would be 2. And that's the only thing I could factor out to try to make it look like this original vector v. But then if I divide out a 4 from 10, I get 2.5. And that is clearly, this right here is not equal to the original vector. So we can also make this argument that if we were to plot these two vectors, that we would observe they do not lie along the same line. There's a rotation and a scale that took place. So 2, 1 is this vector here. But 8, 10, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8, 10 would be this vector up here. And it's going to be kind of hard to draw to make them not look, oh, they don't look parallel. Good, okay, so you can see that this is the 8, 10 vector, and there was a rotation that took place and a scale effect. Whoops. Well, you get the idea here. And this vector here, 2, 1, so we didn't, in fact, just scale the vector. So the vector 2, 1 was scaled and rotated. And by definition, an eigenvector is one that only gets scaled. Now, it turns out that that eigenvectors are not unique, that you can find more than one eigenvector. So we earlier argued that 1, 1 was an eigenvector, but we could have tried 2, 2, or 3, 3, or 4, 4, or any vector where the x and y components are the same. And let's just show that for any non-zero real number c, that CC will be an eigenvector of the 2, 4, 4, 2 matrix. So if I multiply these together, what I should see is, okay, I'll take c times 2, 4 plus c times 4, 2. I will get 2c plus 4c is 6c, and 4c plus 2c is 6c, and already I could see that I could factor out a scalar of 6. Therefore, this is an eigenvector, this is the lambda, and it's the same as the vector that went in, just scaled by a factor of 6. So lambda equals 6 is the eigenvalue of any eigenvector v equals cc. And we can make the same argument for negative c and positive c, that would also be an eigenvector. But I just want to make you aware that there's more than one possible eigenvector. The important part is they should all maintain the same ratio. So 1 to 1, 2 to 2, 3 to 3, 4 to 4 all have a ratio of 1 to 1. And we're going to wrap this lesson up with just saying that every square n by n matrix is going to have n eigenvalues and n eigenvectors. So that means a 2 by 2, if we had a 2 by 2, we would have 2 eigenvalues and 2 eigenvectors. And we're not going to go through how you find these. It would come down to solving the equation AV equals lambda V, solving it for the lambdas and for the V's. We're just not going to get into it. It's not worthwhile, and there's some concepts there that just will turn it into a process, and it'll be hard to make sense of in a meaningful way without really digging into linear algebra. So we just need to find out how to calculate them, and we'll see how they end up applying in the next lesson. So they are values that are vectors hidden in the matrix that give us important features of that matrix. To find them, we can use Wolfram alpha. And so in Wolfram alpha, here's what you would enter in. You do eigenvalues, and you always check your input when it comes out, but we use these curly brackets, one to open and one to close the matrix, and then another pair for each row. So the first row this is for the row, 2, 4, that will give me the 2 and the 4. So those two values are those two values. And this 4, 2, which is now, notice a comma, another pair of brackets, 4, 2, close bracket, that will give us the second row. And then these two outer brackets, open and close our matrix. And lo and behold, here's what we get. We get lambda 1 equals 6. That's the first eigenvalue. The eigenvector that goes with that, it's got a buddy, and its buddy is the vector 1, 1. For the eigenvalue lambda 2 equals negative 2, the eigenvector is negative 1, 1. And we showed this earlier, but we can see that Wolfram alpha will give us the same answer. Very nice. So again, we kind of pointed out that eigenvalues are unique and will be the same across all software. Eigenvectors are not unique, but it is the case that the ratio of y to x across any given eigenvectors is the same from one instance of an eigenvector to another. For instance, if I said that, hey, the eigenvector is 1, 2.7305, and you said, well, no, my eigenvector is 0.34372 and 0.93907. If you looked at the rise to run ratio, in both instances, it's still 2.7305. So it shouldn't be concerning if you use something other than Wolfram alpha and you don't get exactly the same vectors that I do. You can just say, oh, well, I got 5, 5. Well, 5, 5 has a 1-to-1 ratio, just like 1, 1 does. So that's it for this video. In the next lesson, we'll actually get into how we solve differential equations with this stuff. See you there.